Hi, I'm Matthias Kaeding. I'm a PhD student from University Duisburg-Essen. This is about the set cover problem. This is a problem where you basically get a collection of sets which cover a universe, and your task was finding the smallest collection which also covers a universe. By cover, it's just meant that the union of the sets is given by the universe which you're supposed to cover. Yeah, here would be an example. Let's say you have a universe which consists of the letters A to F, and you get a bunch of sets like these simple 4 sets. Then a possible solution would be just to give out the sets 1 and 2, because they cover A to F. And another feature which you can see is that the sets are usually overlapping. So yeah, this is a pretty fundamental problem in approximation algorithm, but it's actually pretty important because you can represent a lot of problems as set cover problem. For example, in location planning, shift plannings, and virus detection. In our application, we had to minimize the number of hospitals in Germany, given that every person can reach one hospital within 30 minutes. Which is a location planning problem. This can also be represented as set cover. And I'm sorry, you skipped a slide. No, the other, sorry. Yes, so the optimal solution is actually available via linear programming, but this is not really feasible for larger problems. So an alternative is given by the greedy approximation, and there was no fast solution in R available, so yeah, this is why I created the RcppGreedySetCover package. And this is fast because it uses RCPP for the algorithm and data table for pre- and post-processing. The actual algorithm works like that. Sorry for all the math. You basically have to look up every time and every step the largest set of uncovered elements. You save this set and you mark the elements as covered. So you basically have to do a lot of lookups, and you need a lot of objects which are dynamic. I mean, which grow and shrink efficiently. So this is why this is not easy to implement in base R, because shrinking and growing objects can be slow. Yeah. So in general, about the algorithm itself, it's approximative, but it's pretty fast. You can bounce the approximation error, but the general takeaway is that if you have a larger problem, then you basically this is pretty much all you can do. Like I said, you have to do a lot of lookups and resizing of objects for the algorithm. The actual elements and sets can be of arbitrary types. These are represented as integers, and the set can be pretty naturally represented as a set from the STD. You need to map the elements to the sets and the sets to the elements. They are both pretty natural representations in C++11 for this. Basically, you can just use this std vector and then std anor.map, and you get a constant time for, or average constant time for lookup and access removal of elements. And you also have to find the largest set of uncovered elements. This is done in the package by using a boost multi-index container. You can query this directly with IDs for which are then hashed, so you get fast lookup by IDs. But they are also sorted by size, so you get an interface where you always get the largest element very quickly. So yeah, all of this is then pretty efficient. This would be our application. The data is basically a 1 kilometer grid of Germany where you have the population and a bunch of other data. This is 1 kilometer grid cells, and you want to find the smallest number of hospitals which can cover every visible grid cells here. And we have, as basic data set, you have just a tidy long data set. In our case, we had to look up all the drive times of all raster cells. And and then you just exclude the ones which have drive times which are too large. And if you do that, you end up with a pretty large data set. So this is around 160 million rows, because it's long, not wide. So this is why this had to be fast. The actually package is pretty easy to use. It consists of a single function called GreedySetCover. And you just input a long data frame, which consists of 2 columns. The first column is always the set. The second columns are always the elements. Like I said, the type can be arbitrary, more or less, because sets and elements are mapped to integers internally. And and this here took like 5 minutes. With this, was fast enough for our application. And the output has a complete same format as the input. It's also a tidy long data frame consisting of 2 columns, where the first column is a set, the second is the element. And here's would be like just a sanity check if it works. So if the solution actually is a cover, and not very surprisingly, it does work. Here would be just a visualization of the results. The red, it's probably not very well visible back in the room, but the red crosses are the found hospitals. And those are distributed among Germany. If you look a little bit closer, then you find out that the result is pretty much driven by sparsely populated areas. Just a few stuff for future improvements of the packages. I think it can be speed up because you have to build a lot of objects. I think you could maybe do it smarter. And also I have a data table dependency. I think I can get rid of it as much as I like the package. And there are some extensions of the basic algorithm which I should also implement, like weighted set cover or capacitated set cover.